Okay, so beginning with question one, if they give you these kind of percentage mass information, anything like this, first thing to do is always to work out the empirical formula. So that's what is done here. So table format's always the best way to do that. So just list the elements, copy down your masses or percentage masses, divide by the AR, and then divide by the smallest of those. And usually that will give you whole numbers. You notice here it doesn't. But if you see 2.5, you realise, well, if you doubled all of them, they'd still be in the same ratio, and then they would be whole numbers. So you just say, right, times 2 will give you 5 and 10 and 2. And that tells you that the empirical formula is C5H10O2. But remember, that's not necessarily the molecular formula. For that, you need the mass spec information. But the mass spec told you that you had a prominent peak at 102. So that's the one with the biggest mass, so you expect that to be the molecular ion peak. And what you need to do is compare that with the calculated MR from this. So you calculate the MR from this formula, and you get 60 plus 10 plus 32 equals 102. And you say that this equals the M over Z for the molecular ion peak in the mass spectrum. But you really need to spell this out. Don't just say this fits with the mass spectrum or something vague like that. You need to write out in proper sort of detail like this, that this equals the M over Z for the molecular ion peak in the mass spec. And that being the case, that means that actually this is the molecular formula because it gives the correct MR. If the molecular ion peak had been at 204, then you'd have thought, oh yeah, that's 2 lots of this, so therefore you'd have had to double everything. But in this case, it fits. So that now tells you that the molecular formula is also C5H10O2. Okay, and you need to make sure in your answer that you've got both those stated, the empirical formula and the molecular formula, and explain clearly how you use the mass spec to get to that point. Okay, so the next step is going to be to look at the infrared. Don't do the NMR yet, because infrared gives you much simpler information, but it gives it in a very straightforward way. So get that sorted out first, because that's going to be helpful then in making sense of the NMR. So the things to look for, first of all, are carbonyl peaks and OH peaks. And we've got both here. So this peak, if we look at its limits, remember to look at the actual limits of the peak, not just vaguely where it is, but that fits with about 3,200 to 3,600, so that tells you that's an alcohol OH. Okay, don't just say OH, because remember that carboxylic acid ones look different. There aren't enough carbons in the molecule for it to be a phenol, so we know that's an alcohol OH. This, remember, is CH, which isn't useful to us, just don't mistake it for anything else. You always get that sharp cluster around 3,000. But this is unmistakably a C double bond O. So again, registering the limits of the peak with your data sheet, you can see it corresponds more or less to this 1620 to 1830, which is what your data sheet tells you are the limits for a carbonyl peak. So we know we've got C double bond O. And there are a couple of other peaks you might look for. We'll see those in some later questions. But as far as this spectrum goes, that's all you can get. This is the fingerprint region. Don't try and interpret anything in there, because you're highly likely to get it wrong, because there are lots of uninterpretable peaks in there. So we now know that whatever structure we get from the NMR, it's got to include an alcohol OH, and it's got to include C double bond O. Okay, so looking now at the proton NMR, there are lots of ways to approach this, but what I would try and do is to try to sort of build up a structure as you work through it, rather than just kind of itemizing information about each peak, because if you don't begin to build the structure up, it can be quite difficult. So my thought with this one would be to start perhaps with that peak, because that has a very characteristic shift. Somewhere there between 3 and a bit and 4 and a bit, there aren't many possibilities, and the one that's compatible with the molecular formula in this case is that that's an OCH peak, okay, because that has the right chemical shift range for that, and there's not much else can be in that region. And of course we know that this compound has an OH in it, so that strongly suggests that we've got the OH there, and that this peak comes from the CH next to it. And of course we now know two important facts that follow on from that. One is that the area of 2 tells you that that's a CH2, but the fact that it's a triplet tells you that there are 2 carbons on the next one. So just by looking at that peak, we can say, right, it looks like we've got that substructure in the molecule. So the next thing I would then do is to say, right, well, if I'm going to postulate that, I need to make sure I've got a peak that accounts for the OH, and I've also got a peak that accounts for that CH2. So the OH is easy because there's only one of it, so there's got to be a peak with an area of 1, and there it is, and you can see it does what an OH needs to do, which is be a singlet. Remember, OH is never split. So that one looks like it's the OH. OHs can have almost any chemical shift, so that doesn't really matter, but the fact that it's a singlet's important. So that fits. That looks like it's the OH. That's the CH2. Oh, now we've got to find the CH2 which must be next to it to cause it to be a triplet. And you can see it could be either this one or this one, but this one would be complicated because if it was split by these two, that would only make it a triplet, whereas actually it's a quartet, so it doesn't look like that fits, whereas this one does fit because it's another triplet, so it would be split by those two. So that strongly suggests that that CH2 gives that peak, whereas this CH2 gives that peak. Okay, now the question is what comes next? And again, the chemical shift is very useful here because it's between 2 and 3. It's not just a bulk standard HCr peak. That means it's next to something interesting. And again, the one that fits that we know about is a carbonyl group because HCCO gives that shift between 2 and 3. So that strongly suggests that we have C double bond O there. Could be something else, could be an aromatic ring, but we haven't got one of those, so that looks like the best candidate. So then we've got this much of the molecule sorted out. Now if we look at the other 2 peaks, you've got a 2 carbon peak and a 3 carbon peak, and you've got a quartet and a triplet, and that is immediately suggestive of an ethyl group because you get CH2, CH3, and that's split into a quartet because of the next door 3, that one split into a triplet because of the next door 2. So that pattern, quartet and a triplet there with those areas, immediately should shout at you ethyl group. And if we look at the chemical shift of that one, again it's in that region where it looks like it's next door to a CO, so we can say this looks like it fits. And that would be suggesting that that CH2 gives you that peak, and that CH3 gives you that peak. All the chemical shifts fit, all the areas fit, and all the splittings fit. Double check that it fits the molecular formula, which it does, and we haven't forgotten anything from the infrared, which we haven't, so that all looks fine. Having worked it out, it's really important you make sure that everything's accounted for fully in your explanation. It's a good idea to do that working out in rough first and then start going through it peak by peak. And a good way to do it actually is just to label that set of hydrogens A and B and C and D and E, or possibly even in alphabetical order might be even better. It doesn't really matter. And then you can just equate those to the peaks and say, right, this one is E, this one is A, this one is B, this one is C, this one is D, so that it's absolutely clear that you know which multiplet comes from which set of hydrogens in the structure, and then make sure you've explained the splittings and the areas and the chemical shifts for each one, and then you'll make sure you get the marks. The final thing is that we've now worked everything out. We didn't make use of the mass spec fragments, and you'll find that's commonly the case. Mass spec fragments are generally only really useful for sort of deciding between two possibilities when there's nothing much else you can do with them. But the trouble is, if they give you that information in the question, you've still got to account for it. So we've got two peaks to account for, with m over z of 31 and 57. So you've just got to go through and break the chain in various places. Remember, the total adds up to 102. So 31 is actually easy to find. Breaking off OH only takes 17 away, that's too small. But if you break it here, if you add up on that side, you get 31. And so that implies that the 31 fragment is CH2OH plus. Okay, remember, you must put the positive sign on to show that it's a positive ion when you identify the fragment. So that suggests that's the 31 fragment. 57, it's a bit bigger, but we know we've got the ethyl group here, adds up to 29, and on the carbon takes you to 41, and then the oxygen takes you to 57. So if we break it here, then that gives 57 on that side. So again, that would mean that we could just write down the fragment CH3, CH2, CO plus as the 57 fragment, and then we've accounted for everything.